think I will be able to cover everything. So I would like to say a couple of words on the multi-fidelity version. And then I'll say, present something on the state assimilation part. So this is my personal view of the multi-fidelity. So other people will disagree. Essentially, I discussed the multi-level estimator that was proposed by Storfer, Wilcox, and Musburger a few years ago. And I tried to link with the multi-level, and so let's start again from the multi-level or the multi-index, because everything generalized is to this multi-index context. So the point in the multi-level is to use this hierarchy of discretizations and use this telescopic identity. So, okay, we want to compute the expected value of the exact Q. We can't do this, so we go to a highly refined level, capital L. So we target this discretization level here, but then we write this as QL minus 1 plus QL minus 1, and hope that this difference is more, so it's easy to approximate by Monte Carlo, and then you could do it recursively. So then you create QL minus 1, the expectation of QL minus 1, you can also write as QL minus 1 minus QL minus 2 plus the expectation of QL minus 2, and you end up with this sum, this telescopic sum. Okay? So if I write it in this way, so I think yesterday I wrote it the other way, so you say let's start with Q0, which is easy, and then we add a correction. Now if I start if you reverse the order, you could interpret this more in terms of control variates. So you want to do Monte Carlo on QL, but then you use QL minus 1 as a surrogate for QL, which gives a good prediction of QL, so that the Monte Carlo part on the difference becomes much easier. So if you're familiar with the control variates, that's somehow the way you do control variates. And so written in this way, one could interpret QL minus 1 as a low fidelity or surrogate model for QL, and then QL minus 2 as a surrogate model for QL minus 1 and so on. So then the idea that this same construction now you could use it also beyond discretization, let's say spatial discretization or temporal discretization. You could think more generally that you have a sequence of surrogate models. So again, you have a high fidelity model, let's say QL, and then you have a sequence of surrogate models, whatever they are, which somehow you are able to order, so by accuracy. And you want to use these surrogate models to accelerate the Monte Carlo construction. Now, if you take this broader point of view, where the surrogate models are not necessarily linked to a discretization of some differential equation, then it's not at all clear whether these consecutive differences become smaller and smaller. They might not. So you might not have a convergence as you have with respect to discretization parameter. Okay, and I could still do some acceleration, but yeah, it might not be smaller, and they might not decay. So what is more common in when we apply this control variate idea is to add an extra parameter, alpha L. So you try to rescale your fidelity model with some parameter, so that it matches as much as possible with the next model QL. That's an extra parameter that you can tune, and you can find the best value of this extra parameter to get the smallest values. Okay, so this is an extra degree of freedom that you can add to the method. It's not done in multi-level because, again, you expect to have this. You could do it multi-level as well, but okay, you add extra degrees of freedom, but you are adding also complexity in tuning this extra parameter. And since you are doing a multi-level with a sequence of meshes, and you do expect to have a grid convergence, it usually doesn't pay off to add this extra complexity, because you know that asymptotically this alpha should go to 1 because this difference is going to 0. But if you do this, take this more general approach with a multi-fidelity and different surrogates where you don't have any guarantee that this difference is small, it usually does pay off to add this extra parameter alpha and try to tune it to have the smallest variance. Okay. So let me just spend a couple of minutes on recording the basic contravariate idea, which is taught in some Monte Carlo courses. So you might be very familiar with this, but if not, this is just a recap. So forget about the multi-level and whatever, and say that you have you target your goal is to compute the expected value of some output Q, which depends on some random variables Y, and that's your high fidelity. So you could do Monte Carlo directly on this. And we have seen this, so you draw independent realization of Y, and then you evaluate your output Q. And you know that mean square error, so this is unbiased, so the mean square error is equal to the variance of the estimator, which is case like the variance of Q divided by M. Now, if the variance of Q is large, you may have to use a lot of samples to have a decent accuracy. So the contravariate idea try to correct or improve the Monte Carlo estimator to reduce the variance. So it's what is called the variance reduction technique. And you do this by using a surrogate model, Q tilde, precisely in the way that I have described earlier. So if Q tilde gives a good prediction of Q, then what you can do is to build a new random variable Q alpha, a new model, that is Q minus alpha Q tilde minus the expected value of Q tilde. And I should say here that for the time being, I'm assuming that Q tilde, the mean of this surrogate is non-exemptive, which might not be the case, but suppose that it's non-exemptive. So if I know exactly mu tilde, then I can build this new random variable, and then I can apply Monte Carlo on this, because the expectation of Q alpha is equal to the expectation of Q, because this is a centered variable. No matter what alpha I put, the expectation of Q alpha is equal to the expectation of Q. But then, so if I do Monte Carlo on Q alpha, then the mean square error will depend on now the variance of Q alpha instead of the variance of Q. So then the question is whether the variance of Q alpha is smaller than the variance of Q or not. And then that's where you have this parameter alpha that you can choose. Okay, so the variance of the estimator is the variance of Q alpha divided by mu. But then if I expand the variance of Q alpha, this will be the variance of Q plus alpha squared, the variance of Q tilde, minus twice the covariance between Q and Q tilde. Okay, which is nice quadratic form in alpha, so you can find the minimum. So the alpha star that gives the minimal variance. And is given by this covariance between Q and Q tilde, so between the high fidelity and the surrogate, divided by the variance of the surrogate. So that's the optimal choice of alpha star, and then you can plug this alpha star into the variance, and you see that the variance, if you use the optimal value, the variance of the estimator is 1 over m, the variance of Q minus this covariance squared divided by the variance of Q tilde. I can just pull out the variance of Q. So that's the variance of Q over m times 1 minus the correlation squared. Correlation between Q and Q tilde, which is always between 0 and 1, and minus 1 and 1. And squared will be always between 0 and 1. And then you see the amount of variance reduction that you can achieve that is related to the correlation between the surrogate and the high fidelity. So if those are highly correlated, this term will be quite small, and then you have a lot of variance reduction with respect to the variance of the pure Monte Carlo. If the surrogate is barely uncorrelated with the target, you don't gain anything. Either you lose because you have to evaluate the surrogate on top of the high fidelity. Okay? So it does actually pay off in general if you have a general surrogate and you're not sure that this difference is small, it does pay off to put this alpha and optimize over this alpha to get the best, the maximum variance reduction. Okay. So this was the standard control variate. Now the question is, how do we do it multi-level if we have multiple surrogates? And then the idea is to do it recursively, as somehow I hinted at the beginning. Again, I want to compute the expected value of Q. Okay, Q and QL is, let's say, they are the same. So QL is the target, is the high fidelity, is what I can, is the best model I can use to do my computation. But then I want to profit of surrogates, which I call Q0 up to QL minus 1. So I do the first variance reduction trick. So I write as expected value of QL minus some parameter alpha tilde L minus 1 QL minus 1 plus alpha tilde expected value of QL minus 1. And I realize I forgot to say something important. So go back, sorry, I go back to the previous slide. So up to here, I assume that the mean of this surrogate was known exactly. If it is not, of course, you have also to estimate this mean. And this might be as costly as estimate the mean of Q, unless Q tilde is much cheaper. So if you don't know the mean exactly, but you have a very cheap surrogate, then you can just estimate this other mean with Monte Carlo with a bigger sample size, and you will still gain in terms of computational cost. Because computing this accurately is relatively cheap. Okay. Good. So in general, you don't know the mean in this surrogate, so you also have to estimate the mean by Monte Carlo. So I do the first step. I subtract alpha tilde QL minus 1, and then I have to add it back again. And eventually I will approximate those two expectations independently with two different Monte Carlo estimates, knowing that the second one is cheaper and I can use a bigger sample size. But then I can do it recursively, okay? So to estimate the second mean here, I can again subtract an alpha tilde Q minus 1 and add it back, and I can go back up to and use all my models in sequence up to level 0, okay? So once I have written this more general telescopic sum, now the idea is to use Monte Carlo estimators for each one of those terms, and eventually try to optimize these parameters. Okay. So now I use Monte Carlo estimators. You have a choice, as I have discussed it, for the multi-level Monte Carlo to use independent estimators or to do this recycling. So whatever, so this one should be the one with the largest sample size because that's the cheapest model. You could also decide to recycle samples, so whatever you have used here, you take a subset and one of those, and then you use it to estimate the next difference, and then you do subsampling up to the end. So both versions are possible. Now, this is not how multi-fidelity is written usually. You can just rearrange terms. So if I rearrange the terms that contain QL minus 1, the terms that contain QL minus 2, I end up with this formula. So I have to compute this expected value of QL, and then some alpha tilde minus 1, this difference between those two expected values is the expected value of the same quantity, but this one is computed with the sample size ML using the same sample as here, and this one is computed with a larger sample size, and this is the one that appears in this second term here. Okay, and then this one again shares the same sample size, the same samples as this one, and this one uses a bigger sample size to estimate the same expected value. Okay. So if I rewrite in these terms here, now I can rename these coefficients. This is alpha L minus 1, alpha L minus 2, and so on. So I can rewrite it in this form, which is the one that is more typically used as a multi-level estimator. Okay. where again, so partly of the samples are shared, if not all of them. It depends whether you use independent Monte Carlo or recycling samples. So this is the estimator that was proposed in this paper here. There is also a Sion review that reviews some ideas on this multi-level framework. And in this paper, they propose actually to reuse the samples. So each one of those Monte Carlo estimators, so you first draw a big sample of your underlying random variables from 1 to M0, which is the largest sample size. And then in each one of those expectations, you just take the first ML terms. Okay. So in this paper, they worked out completely the variance and the cost and the whole optimization. What do you have to optimize? Once again, now you have to optimize the sample sizes in all these expectations, as well as this alpha parameter. And so I have not written the formulas in these slides, but you have explicit formulas. They will depend, as usual, you minimize the variance for a given budget, or the other way, you minimize the cost for a given error. So the cost of evaluating each model will enter as a parameter in this optimization and a driving criterion. And in general, the alpha L, okay, this depends on how you do which version of the estimator you take. If you take this version where the samples are shared among all the differences, then this alpha L, each alpha L will depend on the correlation between QL and the high fidelity one. So every time you compare, you estimate the correlation between every surrogate and the high fidelity. If you use independent sampler, independent Monte Carlo, then you only compare the correlation between two consecutive models. Okay, that's essentially the difference between the two versions, whether you compare estimate the correlation with respect to the fidelity or with respect to the next okay, but I haven't seen this, the optimization done for the independent versions, if you want to do as an exercise. Okay, I wanted just to mention this, to make this link between the two estimators. So you can think of the multi-fidelity as a further extension of the multi-level that uses this extra degrees of freedom, this extra alpha parameter to further reduce the variance in case those differences are not that small or don't decay to zero asymptotically. Yes, so those are essentially the two main reference papers. This one is for the unbiased estimator that I presented first. This one is the multi-index extension, and this one is the multi-fidelity proposed by Hausdorff. Okay.
Sorry, can I just ask something? I was wondering whether you've seen that someone has done a comparison between, for some problem between the multi-level and the multi-fidelity, like how it performs at the same problem, like which one of the methods would actually, for the same cost, give smaller...
No, it should be done.
Right?
I mean, to me, there are even further extensions, but at least, to me, there are at least 4 versions. This one with independent estimations, so with recycling, or the same but just fixing alpha to 1 and without. The comparison is not, and it should be done carefully because you can compare in terms of asymptotic rates. I haven't done the calculations, but I believe that if you are in the multi-level setting and you do have discrete convergence, this alpha eventually will go to 1, so I think you get the same asymptotic complexity in the two cases. Now, from a practical implementation point of view, of course, setting alpha to 1, optimizing alpha will give a smaller variance than setting alpha to 1. So if you knew the ideal optimal alpha, you would get better results. But in practice, you don't, so you have to estimate. And then the question is, what's the amount of work you have to invest in estimating those alpha, and does it pay off in terms of overall? Yeah, I don't have an answer. I haven't seen this fair comparison. It should be done fairly in this sense. So just defining what is exactly the algorithm and the adaptive algorithm that you use to estimate all those parameters and see whether one is more performing than the other.
Yeah, thank you. Because to me, it's not obvious that this performs better at all. Like, because exactly of what you said, like you might get some improvement, but you also have to invest more.
Yeah.
So like, and for if you have a standard multi-level, like, and you are in this kind of multi-fidelity setting, so you don't have hierarchy of meshes, you can do like then the bias essentially doesn't play a role anymore. Like you don't care about the bias because the bias is just your high fidelity model, and then you just optimize the samples, the sample sizes. So you can do that, and you can of course ask whether like which of those methods performs better. Yeah, that's really interesting.
I should say, so I didn't have time to add to these slides, but there are further extensions of the multi-fidelity that was proposed. And as a matter of fact, so first, this one is still somehow not too far from the multi-level in the sense that you assume that you have a hierarchy of surrogates that you can order, and you know what the ordering is, which also is not the case in many applications. You can also, if I go back to this just simple control variate idea, we could say if, what was it? Here, sorry. If I have two surrogates, we can either try to do this hierarchical construction if I know that one surrogate is more surrogate than the second one. But if they are competing, so I can't establish an order, what you can do is just put them together. So you build a new Q with two parameters, alpha 1, alpha 2, where you subtract both both surrogates at the same time. And then you try to find the optimal alpha 1, alpha 2. You can think of this as a regression problem, essentially. You're trying to regress Q using the two surrogates. So the alpha 1, alpha 2 are exactly the regression coefficients. So you're trying to find the best fit of Q using the two surrogates. And this corresponds to the estimator with the smallest variance. Okay, so you can put them together, and they somehow the regression coefficients alpha 1, alpha 2, they give an indication on which surrogate is better. If one regression coefficient is nearly 0, it means okay, this surrogate, just forget about it, it's useless. Okay, so if you can also take this regression point of view where you let somehow the method discover automatically, and the optimal alphas will be related to the mutual correlations of each surrogate with a target with a high fidelity. So essentially, you let the method discover which surrogates to use and which linear combinations of surrogates to use to get the best variance reduction. And then, of course, you can combine everything together, so you can take different linear combinations. Yeah. Thanks for the question. Are there other questions before I switch to the next topic? Okay. So as I said in the last part, my idea was to propose some more advanced applications of multi-level. So again, I decided to go with this data assimilation. It will be much more research style, so not many details, just to give you a flavor of the idea on how one can use multi-level methods in other contexts, in data assimilation, and those are not so straightforward construction of multi-level methods. So the first problem I discuss is a filtering problem, and in particular multi-level ensemble Kalman filter. So if you are not familiar, this is a very brief recap on what filtering is. So suppose you have, so filtering is principally related to dynamical systems and try to track the evolution of a dynamical system using observations that come over time. So suppose you have a dynamical system, could be deterministic or stochastic, doesn't matter too much, but in general you don't know exactly the initial conditions, so I assume that the initial condition is random, so you have an initial probability measure describing possible initial conditions, and then this probability measure is propagated by the dynamical system, so it will evolve in time. And now if I at some point in time I receive an observation, I can try to condition this probability measure to the observation, and hopefully I will reduce the uncertainty. And now you restart the process, now you have reduced the uncertainty in the new initial condition, you propagate again through the dynamical system, you get another observation, and you reduce again the uncertainty. And if you have enough observation, you hope that you are tracking decently the evolution of the system. Typical example is weather forecasting on hurricane tracking, so you try to forecast where the hurricane will hit the land and so on. So you receive observations at discrete times. Those are not related with the time discretization of the dynamical system. So just so every day you receive the observations and whatever. So the observation is some observation operator on the state of the system. So usually you don't observe the whole state, you only observe something, the value at one point. You launch your balloon in the sky and you measure the whatever pressure, temperature on that column in that point. And usually these observations are polluted by noise. So it's the noise in the observation. They call Y these observations. UN is the state at time Tn. Capital Yn is the collection of the observations up to the time n. And then I define the solution operator that transforms UN minus 1 into UN by just solving the corresponding dynamics. So if I know UN minus 1, I can propagate and find UN. Okay. Of course, in practice, since I want to bring multi-level ideas, so I cannot solve the dynamical system exactly. You need to discretize in time and in general in space as well if it is a PDE model. So there will be some underlying discretization, and I just suppose that I found one I'm happy with, and they don't with capital L is the level of discretization I'm happy with. So in practice, one will compute this UN capital L. And then the goal is to approximate this filtering distribution, which is, as I said, the distribution of UN or UNL conditioned on all the observations that you have collected up to time n. So this is different than what is called the smoothing distribution. In the smoothing distribution, you imagine that you observe on the whole time, and then you may go back and correct the distribution also with respect to future observations. If you want, for instance, to reconstruct the initial condition once you have observed everything. But in the filtering, you just evolve in time, so you don't correct the past. You just try to correct the current state based on all the observations that you have observed up to time n. Okay, and typically, this you can write down this evolution. So the idea is to write an evolution of this filtered distribution. This is what you're after. So you're trying to track this filtered distribution. And you can do it in two steps, conceptually. So suppose that somehow you have computed the filtered distribution up to time n-1. When I say computed the filtered distribution, it means that maybe you have an ensemble of particles that is distributed according to the filtered distribution. Or you can write somehow a dynamical system for, modified dynamical system for that has this filtered distribution. Okay, so suppose you have a random variable u, random state u n-1 that has this filtered distribution up to n-1. Then you will have to propagate this distribution through the dynamical system up to the next time step. So this is called the prediction or the forecast. So you just use your model to predict what will be the distribution of the state at time n. So, and this is just governed by your solution operator, by your dynamical system and the solution operator that propagates this measure into the measure of the state. But then at time n, so this is what is the filtered distribution, so this will be the distribution of un, still given the observation up to time n-1, because we have not included yet the new observation. But now at time n, you have a new observation that arrives, the little yn. So then you want to add this observation to your observation process and condition this distribution here to the new observation. Okay? And this is what is called the analysis step. It's further correction, and then you correct this.
So how different is it if you were to add the eta in your P model, for example, if you just added the noise in the model?
It doesn't change anything in the setting, in the sense that this solution operator will be a random solution operator, but it still transforms a measure into a measure.
Yeah.
There will be some diffusion effect if you have the random motion, so your distribution will spread because of the diffusion part. You can, this operator or this dynamical system can be stochastic. Okay, sorry. Yes, it can be stochastic. If you want to use the setting, it should be Markovian. So it forgets in the past, so you can restart the argument. If it is not Markovian, it's more complicated. In particular, you cannot really play this game if you have random coefficients in the model. I mean, if you have random coefficients in the model, those have to be treated separately. So for each value of the coefficient, you could do this filtering, and then somehow you average over those values. But this works well if you have a stochastic differential equation where you have a driving Markovian process, and then you have this memoryless structure. Other questions? Okay. So I don't know how familiar you are with this. I don't give any detail, but if your dynamical system is linear, so meaning that dtu is some linear operator acting on u plus maybe some forcing term plus maybe some again some noise term, and your u0 is Gaussian with some mean 0 and some covariance C0, then the distribution of the state at every time will be Gaussian, just because if you apply a linear operator to a Gaussian, it remains a Gaussian distribution. And if you add the Gaussian noise, it remains Gaussian. Okay, so this linear setting with initial Gaussian distribution, the forecast distribution will always be Gaussian. And if I assimilate measurements and we have Gaussian noise, if you condition a Gaussian distribution to a Gaussian random variable, the conditional distribution is still Gaussian. And you can work out, and there are closed formulas to express the conditional mean and the conditional variance when you condition to some Gaussian distribution. And this is known as the Kalman filter. That's exactly this. So both both the forecast distribution and so this one, and the update or distribution, the filter distribution are Gaussian. The mean and the covariance of the forecast are just dictated by the dynamical system, so how the Gaussian distribution evolves when it goes through this dynamical system, whereas the mean and the covariance of the filtered one, that's where you assimilate the measurement. So that's how they change because of the observation. And this second step is given by the Kalman formula. So the mean, with respect to, as I said, the mean of the forecast, you can just work out the formulas, how it evolves. Once you have the mean of the forecast and the covariance of the forecast, then to get to the update to the filtered one, so the mean of the filtered is the mean of the forecast corrected by this operator here, plus this innovation part, so the observation that you have observed. You can rewrite, maybe I should have rewritten in a different way. So the mean is the mean of the forecast plus this matrix K Ln applied to Yn minus H M N N. And rewrite in this way. This is called the innovation. Essentially, and the H times L is your expected value of the observation based on the model. So you compare the outcome of your model with the measurement, okay, and then you take this difference, this innovation, multiplied by this matrix to correct the mean. And this matrix is called the Kalman gain, and has this expression here as a sort of sure complement of the forecasted covariance with respect to the observation operator, plus the observation, the noise, the covariance of the noise. And the covariance modifiers as well. Okay, anyway, beside the formulas, you have closed formulas to compute everything, except that in high dimension you might struggle because this covariance is maybe huge. Maybe you don't want to apply those directly. Okay, so precisely, if you are in high dimension, this is not really useful because the covariance is too big. If you have a nonlinear problem, this is not usable either because those are valid only in the linear case. So the ensemble Kalman filter addresses those two issues by essentially replacing the covariance, replacing the exact distribution, Gaussian distribution, by particles. So you sample from the Gaussian distribution, you let particles evolve, and then you compute the mean and the covariance by sample mean and sample covariance. And then you use exactly the same update rules, but using the sample mean and sample covariance. So in the ensemble Kalman, it's pictorial. I don't give, no, yes, you have the formula exactly. So you suppose you have come up with an approximation at time n-1. So I should say that the ensemble Kalman filter in the case of nonlinear models doesn't have any guarantee, but it works well in practice. Doesn't have any guarantee because when you do this update, essentially you are approximating the measure with a Gaussian, but the true filtered measure might not be Gaussian, it might be far from Gaussian. So you systematically make this error in the assimilation. If your filtered distribution stays sufficiently unimodal and close to Gaussian, actually it works very well in practice. Better than other methods that are consistent with the true filtering distribution, but then they struggle more like particle filters if you are in high dimension. So it's very popular and widely used. So suppose you have somehow a particle and ensemble that gives a good approximation of this distribution, filtered distribution at time n-1. Then you let those particles evolve through the dynamical system and gives the new ensemble at the new observation time. So here you have the particle at time n-1, and you let them evolve through the dynamical system up to the new observation time, which is here. And now, at this observation time, you want to assimilate the new measurement. And so what you have to do is to fit sort of Gaussian distribution, so you compute the conditional mean and the conditional covariance, the mean and covariance out of your ensemble. And I call this covariance C and L. This is the sample, the empirical covariance based on the ensemble. And then you use these update rules on each particle. So essentially this rule here you apply it to each particle in the ensemble. So the new position of the particle will be the old position plus this innovation term. And to get something that is consistent with the ensemble, with the Kalman filter in the Gaussian case, you have to actually have to perturb the observation. So you take your actual observation and you add artificially noise to that observation for the ice particles. So for each particle you add extra noise, and then you can prove that this in the Gaussian, linear Gaussian setting, this approximation is consistent. So in the limit of infinitely many particles, you recover the pure Kalman filter. Okay? So that's the, here it was nice movie, so I fit the covariance, I receive the observation, it's there, suppose you observe the full system in this case. So intuitively I should move the ensemble toward the green point, and I'm taking into account that there is some noise, so the green is not perfect. And then you use this formula, with the new ensemble, and then you start. Okay? And so in this type of computations, you are after this filtered distribution, and then you might want to compute some output quantity. Let's say you want to compute the expected value of some output Q with respect to this filtered distribution, which you are describing with this ensemble of particles. Okay? So eventually you are after some posterior expectation, or some expectation with respect to this filtered distribution. Could be the place where the hurricane is hitting Florida. Okay? So now the question is, okay, in this setting, can we bring some multi-level ideas now? So we have to approximate the dynamical system. So I've shown here that I use a very accurate approximation of the dynamical system, but can I profit of coarser discretization to reduce the variance and so on? And one possible approach is not the only one, but you see that in this algorithm, there are expectations appearing. One is here in the final outcome, but the other is here in computing the covariance matrix. So okay, let's try to do in the multi-level fashion. So let's try to compute the covariance using a multi-level formula. Okay. So this idea was proposed first for ODE systems in this paper by Akonol, Codillo, and Roltenfon in 2016, and then we did the generalization to space-time processes in this other work in 21. So I don't give the details, I just try to describe the algorithm, how it works. Again, those particles, now I use multi-level idea, so I have several levels. Each level you could think has a different spatial discretization and a different temporal discretization. You can play with both. By the way, there are more recent papers doing a multi-index version of this, where you refine separately space and time. For the time being, I stick to a multi-level, so just one hierarchy of models. I hope you see the picture there. So what I do now is to draw a multi-level ensemble. So now I have a bunch of particles. So the size of the particle relates to the cost. So small particles are light, cheap, and big particles are heavy and costly. Okay. So using the standard multi-level philosophy, I start with a level 0, and I draw a lot of light particles. So those are the little blue ones. Okay. So first idea, I tried to do a filtering using an ensemble of coarse particles, but then of course this would be inaccurate, so I have to correct. So to correct, I have to go to the next level, but then I should evaluate differences between level 1 and level 0. What does it mean, differences? It means that I draw now coupled particles, so particles that live, that are correlated. So I will have one particle at level 1 and a twin particle at level 0. They could maybe initialized at the same value, but then they will evolve according to the two discretization of the dynamical system, so eventually they will separate. So those are the green and blue. You see they are almost overlapped, but not all of them, so here it's a little bit. So those are twin particles. So I have the particle in level 1 and the twin particle on level 2. And then you go on. Then you go to level 2 minus level 1, so those are even heavier particles. So those are the red and the green. Again, there are fewer of those. Okay? So you have this multi-level ensemble, which is all the collection of all those particles, twin particles, okay? Except for the level 0, where I just have a simple ensemble. And of course, I will have to play with the sample size. Once again, I have to decide how many particles to use in each level, with the idea that I use many particles in the cheap level and very few particles in the heavy level. Okay? And then I let those particles evolve, let's say from n-1 to n. So the twin particles evolve, but with a slightly different solution operator, because I have different approximations. So the particles at level L will evolve with the solution operator at level L, and the twin particle, which is close by at level n-1, will evolve with the other approximation. Okay? Then I get to the forecast at step n. I have my multi-level ensemble, and then I can use it to, okay, pictorially, because they are evolving. Of course, during the evolution, they get more apart, you get the new observation time, and then I have this nice multi-level ensemble, and I can use it to estimate the covariance in a multi-level fashion. So it's a telescopic sum using all those collection of ensembles. Okay? This gives an estimation of the covariance, hopefully more accurate, or let's say maybe as accurate as if I were using all the particles in the finest level, but cheaper because many particles have been thrown to coarser levels. Yes.
So I have a question. What if the underlying dynamic is Markovian? What if it's like one of several steps of some MCMC method? Is that have you considered that case as well? And how would you move the particles in a coupled way?
I partly discuss next part.
Okay.
So how would you move the particles in the next way? Suppose that your dynamics is a stochastic differential equation. I would move using the same realization of the Brownian.
Yeah. No, I was more like if it's like if you have to do like an accept reject.
Okay. Next part. Okay. If I have time. Try to hit. Yes, if you have an acceptance rejection, that's a nightmare. Yes, we have to try to couple the acceptance rejection that has problems. Here I'm more thinking that I might have a stochastic dynamics that is with an explicit driving noise, and then I can use the same realization of the driving noise to evolve the twin particles. Okay. There is another important point. What if the system is chaotic? Because then those two twin particles will go far away depending on the Lyapunov exponent, and there's also a problem for these multi-level constructions. So if you have a chaotic system, making those particles to stay together is intrinsically difficult. There are tweaks that you can do. For instance, with SDEs, you can try to add a sort of coupling term, sort of spring that keep those two particles together. But this will change the underlying law of the process. It means that when you compute the expectation, you have to do an important sampling to correct of this change of measure. So this has been proposed by from a paper by Giles and some, I don't remember the co-authors. It works, but then you have to see how this important sampling, this likelihood ratio behaves, because it might explode if the corrected measure is too different from the true measures. Yeah, it doesn't work all the time. So now we have a good multi-level estimation of the covariance, and then we just use the standard update formulas for each of the particles on each of the levels, and then restart the process. Okay. And then we can use the same multi-level ensemble to estimate this output estimation. Okay. So that's the idea. It's involved in the plain multi-level Monte Carlo. We did do some analysis for this. I don't give the details. Is in those two papers. You have to go through some propagation of chaos results, so you essentially compare the particle system with the mean field limit with particles from the mean field limit that use the same realization of the noise, and then you use the properties of the operator. So I assume that this operator has, again, assume that some convergence on the solution operator when with respect to the discretization parameter to some power beta, and then essentially we were able to prove that reasonable assumptions you could get the same type of complexity that you have in standard Monte Carlo. Okay, don't go farther than this, it's just to give you a flavor of the application. And there is again the typical multilevel Monte Carlo improvement with respect to just doing plain ENKF on the finest discretization. Okay, this was just an example with a stochastic differential equation, a simple stochastic differential equation with some colored noise, where we did a spectral discretization of the SDE, so in Fourier modes, and used an exponential order method to integrate in time. Again, hierarchical, but multi-level, not multi-index. And we did observe numerically this improvement. So here you have the cost here and the error, mean square error here. So again, this is very typical for this type of multi-level. If you are after very coarse tolerances, you usually don't have particular gain with a multi-level, so a single level is performing better. But if you want more stringent tolerances, at some point the multi-level has a much better asymptotic complexity than the single level. So just to mention, in this version of this multi-level ENKF, we updated, we computed a single covariance, a single Kalman gain. You could also go more decoupled, where essentially each particle on each level computes its own Kalman gain, and then you just put the particles back together when you want to compute this expectation here. It's a more decoupled way. It means that maybe it's also less good for filtering if you have to correct significantly your ensemble. You could go strongly coupled or weakly coupled. So the other case I wanted to discuss is when you want to do Bayesian inversion and you want to do use some multi-level Markov chain Monte Carlo to sample from a complex posterior distribution. And again, the question is, can you do it multi-level? So it's just a nice picture to say the Bayesian inversion is important and relevant in many fields. What I described here was related to a project from Seismic, although we didn't go very far on the application side. Like, let's say you want to reconstruct the source of an earthquake based on some surface measurements and some sort of so you might want to reconstruct the source, or you might want to reconstruct also the structure, the subsurface conformation based on the measurement on the surface. This means that the forward model, you place a source here, you solve the elastodynamics equations, and you predict the measurements. So this you can, of course, you have to solve elastodynamics equations so in a complex medium, so you have to discretize in space and in time. So you can well imagine to build a hierarchy of discretizations in space and in time to use this forward model. Okay, of course, the finer the grid, the better will be your prediction of the measurements. Now in the Bayesian inverse, you want to reverse, so you want to actually find the source or the material properties that have generated the observations. So again, this is the forward model, given the parameters, source and material. You solve for the elastodynamics equations, so you will be your solution. And then based on this solution, you can compute the values of the probes on the surface. Okay. Now in the Bayesian setting, I don't know how much familiar you are with the Bayesian setting. Essentially, you want to do inference on this parameter theta, and you do it in the Bayesian framework where you assume a prior distribution of this parameter theta. So that's the prior distribution based on some prior knowledge, so some information that you have to put in the prior. Now, if this is a random variable, then you can write down what is the joint distribution of y and theta. Okay, because from theta I can compute u, that's a deterministic model. From u I can predict y. Okay, and then the actual value is 1 plus the noise. So I assume that I know what the distribution of the noise is, let's say Gaussian with some coordinates. So I know what the distribution of the noise is, and I can write down the joint distribution, which will be the conditional distribution of y given theta times the distribution of theta. But now, so this is a joint distribution, but now I know y, that's my actual observation, so I can rewrite this as a conditional distribution of theta given y, okay, and that's what I am after, this posterior distribution, which is this conditional distribution of the parameter given the actual observation, okay, which you can write it down in this formula, but usually you don't know the normalizing constant because it's a complex distribution. And once you have this posterior distribution, then you want maybe to predict some expected outcome, expected output Q with respect to this posterior distribution here. Okay. However, generally you don't know how to sample independently from this posterior distribution because that's a complex object. Okay. So the reference, and of course, you don't have access to the exact U, so you will have here to use your discrete approximate model UL. Okay, and maybe you can build a hierarchy of models, of discretized models here, and for each discretization. So this discretization will enter here in the forecast of the measurements. It means that each discretization will give a different posterior distribution. Okay? So now if I use my discretized model, instead of computing exactly this expectation, I compute, even if I were able, even if I was able to compute exactly an expectation, it would be an expectation with respect to a wrong measure because of this discretization parameter. Okay? And on top of this, I cannot compute this exactly and I have to use Monte Carlo or approaching Monte Carlo, so a double approximation. So the reference algorithm is a Metropolis Hastings MCMC. I guess many of you have seen this, where essentially, so again, I don't know how to build independent realization from this posterior distribution, so the idea is to build a Markov chain that has this posterior distribution as an invariant distribution, and then run the chain long enough, hopefully the chain is ergodic, so I can estimate the expectation, this expectation here, just as an average over a single realization of the chain. The chain being ergodic, eventually all the iterations will be, asymptotically will be distributed by the current distribution. So I can just use, say, the standard Monte Carlo formula, but here those theta I plus b, those theta are actually the successive states of a Markov chain. So they are correlated because of the Markov chain structure. And it's typical the case that so this chain is only asymptotically distributed as the right distribution. So it's a good practice usually to throw away the first leg that is too dependent from the initial point of the chain. So that's why I have a plus b here, that's called the burn-in. So I start averaging only from b plus 1 on. Okay. And how does it work, this Metropolis-Hastings algorithm? So you have to construct a chain that has that measure as a target invariant distribution. And the construction is surprisingly simple. So there's a surprisingly simple way of doing this. That's a Markov chain. So you have to build a rule from starting from, let's say, the state at the ith step to construct the new state of the chain. Okay, suppose that we are at step I. So I have already run my Markov chain up to step I, so I know where I am in theta. So this is a chain in the parameters. So I'm evolving the possible source location, and I try to get an empirical description of this posterior distribution by looking at the states of the chain. Suppose I am in a certain position, then I want to find the next state. So I would like, in principle, to use a Markov transition kernel that gives the next state with the right distribution, but it's almost impossible. So the idea is to use a proposal, what is called a proposal density. So okay, I decide on some rule to draw a new point. Easiest one would be, for instance, to draw from a Gaussian distribution centered in the current position. So I'm probing, I'm evolving the possible source locations by Markov chain. So I ended up here, and then I draw from a Gaussian distribution around that point, and this gives a new proposal candidate. But if I just use that one, will not have the right distribution. So on this proposal, I have to run an acceptance rejection. I decided whether I accept the proposal or whether I reject the proposal. So P is this proposal, and then the acceptance rejection is based on this alpha. So essentially, if I use a Gaussian density, it's symmetric. It means that the probability of going from the current position to the new position is equal to the probability of going from Z to theta I, by symmetry of the Gaussian kernel. So if you use a symmetric proposal, this factor is actually 1. So you only have to compare essentially the probability of the target density in the proposal versus the probability of the target density in the current state. Okay, so the assumption is that this complex posterior distribution, I can evaluate it up to this normalizing constant. But I do have access to this because I can evaluate the proposal. I've chosen this, and I can evaluate my model. So I can evaluate here the density of the noise. Okay, up to this normalizing constants, which I don't know. But since in this algorithm only ratios of P appear, I don't care about the normalizing constant. That's the beauty of this algorithm. You don't need to know the normalizing constant because you only compare probability of states, ratios of probability of states. So I said in the symmetric case, you only have to compare those two. If the probability of the proposal is higher than the probability of the state, of the current state, you accept, you move. Because that's a good proposal. If the probability of the proposal is lower, you only accept with a certain probability. So the probability of acceptance is given by this ratio. That means that if you ended up in a point which is a very low probability, most likely you will reject, but there is still a little bit of chance of accepting. And then you can And that's the criterion to generate the point. If the kernel that you use is not symmetric, then you have also to add this ratio, otherwise you will not get the right distribution. So that's the algorithm, that's the rule, and then you can run it. Okay? Of course, the performance heavily depends on how good is your proposal, because if you propose crappy points, you will keep on rejecting it, it barely doesn't move. Okay? Good. And of course, the issue here is that, yes, we can evaluate this density, but evaluating this density is costly because it implies solving the model. So, given a candidate theta, I have to go and solve my elastic dynamics to be able to compare with the measurements and evaluate this. So that's where you might want to bring multi-level ideas. So, okay, do I really need to compute this? Evaluate this density with the finest discretization level? Could I profit on coarser discretizations, okay, that are cheaper, okay, give a worse approximation of this posterior density, but maybe I can do something. So if you want to bring multi-level ideas, well, once again, the idea now is to construct a sequence of approximations, so discretizations, again, the geometric sequence of refinements, knowing that for each one of those levels, you will have a different posterior distributions. Okay? So pictorially, if you want to, let's say, identify the source location, this could be the distribution of the source location. Red is more probable, blue is less probable. Okay, and this will be sort of coarse. I mean, it's just a pictorial. Doesn't necessarily mean, but this could be the approximation of the coarse level, and then you refine more and more, and you get a more accurate approximation of this posterior. So, how do we build then our multi-level construction here? Well, the main idea is from this paper by Rob Scheichel, Rita Teckentruth, Nodwell, and Hedelsen from 2015. So we are after the posterior expectation, so we're going to compute the expectation of Q with respect to this posterior distribution, but this is inaccessible. So, okay, we can replace this with the expectation with respect to the posterior and the finest discretization level. And then I try to build a telescopic sum. So now I write this as a posterior with respect to the coarse discretization plus the first correction term, plus the second correction term, and so on. But notice now that those expectations are with respect to two different measures. Okay? Because the posterior measure is different whether I do it on level 0 or level 1, and so on. So this is an equality, so I use this telescopic identity, and now I want to replace each one of those expectations with MCMC estimators. So I have to build Markov chains and replace the expectation as a sample time average of my Markov chain. So this will be the final estimator. So this first will be my MCMC estimator for the first term here. It means that I have to construct a Markov chain that asymptotically has this distribution here. Okay, and then I average over the Markov chain to get an expectation of the first term here. Then I go to the next level, so I compare the level L and the level L-1. So I want to evaluate any of those differences. This means that now I have to build two Markov chains. One that targets the distribution at level L, and the other that targets the distribution at level L-1. And this is important because this sum has to be telescopic. If they both target the same distribution, it will not telescopic, then you don't have this. So those are two different Markov chains that target two different measures, which I use this one to estimate the posterior expectation at level L, and this one to estimate the posterior expectation at level L-1. Okay? But remember that in the multi-level construction, this is effective as long as this difference is small. And it gets smaller and smaller when I go to final level. If this difference is not getting smaller, I don't gain anything with the multi-level. Okay? What does this imply? This implies that the two chains that I use here have to stay strongly correlated. Because if I use two independent chains, the difference is not small, so there is no gain in multi-level construction. So now here is the whole game. Now I need to build coupled chains, or you can think a chain in a double state. Okay, so now I need to work with pairs, a little bit like in the ensemble, multi-level ensemble filter. So now you have twin particles, one that lives on level L and the other on level M and so on. And those should be evolved in a correlated way and stay somehow close by. But they are targeting to different measures, slightly different measures. I mean, you expect that when L goes to infinity, the difference in those two measures becomes more and more. But that's where the point that Joseph raised. How do you do this? Because here it looks more complicated, and it looks more complicated because of, if you want to use this MCMC, this stochastic, you have an acceptance rejection criterion. So somehow to build these chains that target the right distribution, you draw a proposal and then you accept or reject. And suppose you draw some proposal, the two chains, each one propose something, and then each one runs an acceptance rejection, and then you end up in a situation when one accepts and the other rejects, and then immediately the difference is not small. Okay, and from that point on, the chain may depart completely. Okay, so how can you do a multi-level Monte Carlo in this context, keeping those two chains together? So there are several ideas. I discussed one which is essentially strongly related to this original paper by Schöckel and Marita. There are others that use the importance sampling strategies, so they build good coupled chains, but they don't target exactly the right distribution, and then you have to use importance sampling to correct afterwards. So here it is, again, it's a description. So now we want to build this whole multi-level framework. So we have a first chain that targeted level 0. Okay, here I can use my standard MCMC. But then I have to build those coupled chains as 0, 1, 1, 2, 2, 3. And those chains should stay together, strongly correlated. And hopefully they should also mix faster. So I didn't mention mixing, but the efficiency of MSCMC is strongly related on how the chain forgets about the past, so you get more and more nearly independent samples over the path. So hopefully, if I have a good way of coupling those chains also mix faster, so it means I can use a stronger, shorter burn-in and a stronger, smaller chain, because on the one hand, the difference that I'm evaluating is smaller, so I don't need to get a decent accuracy, don't need a big sample, but hopefully it's also mixing faster, so I can have even a gain in this. So one way of doing this is what we call the independent sampler. Okay, let's try to do this. I have those twin particles at a certain stage. Let's try to come up with an algorithm where both chains propose the same proposal. So, okay, both they propose the same state, and then each one of those decides to accept or reject according to the usual criteria. Okay, so it may indeed happen that one accepts and the other reject. Okay, but if they both accept, then this difference. Okay, here I put an index L also on Q, meaning that maybe there is an approximation also in evaluating the Q. But suppose that there is no discretization, I can evaluate the Q exactly once I know, once I have solved my problem. So if there is no approximation in Q, if both chains propose the same value, this difference is 0. Okay, and remember that I need this difference to be small in variance. Okay, so Again, if they propose the same state, if they both accept the difference is exactly 0, if the one accept and the other reject, the difference is big. Okay, for how many iterations it stays big? Because now the chains are desynchronized. So now again, the two chains are in two different positions and they propose the same state. Both. Okay, well, if they both accept, they resynchronize. And then the difference is 0. Okay? So the difference remains big if, for a few steps, the two chains both reject the state once they have desynchronized. But if the state that I propose is a good state, there is a high chance that even if the two chains are very far apart, both chains will accept the new state, and then they're resynchronized. So you might still have that the invariance in mean square sense, this difference is small, even if for a certain time the chains desynchronize, as long as the probability that they synchronize is sufficiently large. Okay? So, okay, then the whole game is to come up with a good proposal. Okay? So then the general idea is that, okay, let's try to learn the proposal from the previous levels. So I run the chain here with a standard MCMC, and then I have a pretty good, if I run it long enough, I have a pretty good idea on what the posterior distribution is at level 0. Okay? I can use just the empirical distribution, or I can maybe use some kernel density estimation out of it, or I can fit some other model. You can build a generative model that uses this sample to build a generative model from that posterior distribution. Okay, let's use that posterior distribution as a proposal for the next level. So that posterior distribution will be a very good proposal for this level 0, hopefully not such a bad proposal for level 1, because level 1 is not too different from level 0. And then I run the second stage for a certain time, and then I have enough samples here to learn this distribution at level 1. And then I iterate. Now I fit a generative model from this sample at level 1, and then I use this as a proposal. This is called an independent proposal because those chains propose a new state independently of where they are, and that's the key point. Even if they are far apart, you want that the new proposal is the same for both. Okay. Yeah, so that's essentially the idea. And the rationale is that this learned proposal should become better and better, and eventually in the finest levels is almost equal to the target. The two targets are very close by, and the proposal is also very close, so the last stage should almost always accept and should mix very, very fast. Notice, being an independent proposal, every time you accept, you're completely independent from the past. So you're essentially independent. Okay, so that was essentially it. The original paper by Rob Scheichel, they just used the empirical distribution essentially, or no, actually even subsampled from the distribution of the previous chain. What we proposed in this more recent paper was to build this generative model, not just subsampling, but they either fit a kernel density or some other generative model to allow these points also to move and not to stick exactly from those that you have generated at the previous level. Or you could do some Gaussian approximation, so you have a cloud, you just compute mean and covariance and use as a proposal a Gaussian that is centered in the mean and with the right covariance. I mean, you can play with these different dipoles. As I said, you can also use fancy machine learning, optimal transport, or normalizing flows to build a generative model from the sample of the previous level. Some theory, so there is the result in Rob's paper on the complexity of this multi-level MCMC. This assumes that you have this type of decays of the expectation between the posterior at level L and the true posterior, and assumes that the variance is also decay. Now the variance is with respect to this invariant distribution of the joint chain. Okay, so hidden in there is this playing with a coupling between the two chains. So I assume that the chains, these coupled chains are geometrically ergodic, so they do converge to some limit invariant distribution, and this limit invariant distribution has the right marginals, and that this variance of the difference decays in a certain way. And then based on this, you can work out, it's slightly more complex than the standard multilevel Monte Carlo, but you work out a complexity analysis and you get a very similar complexity as in the plain multilevel Monte Carlo. Okay? What we did in this other paper with my former student Juan Pablo and Raul Tempone is to show that indeed if we use these independent proposals, we do verify these assumptions here. So if you build a proposal, sequence of proposals that satisfy certain technical assumptions, partly listed there, I don't go into the details, you can show that indeed this couplet chain converges to a limit invariant measure. Geometrically ergodic means that the convergence is exponentially fast. So actually, it's quite efficient. And this variance of these differences does decay at a certain rate. So we could somehow verify all the assumptions in Rob's paper. So this was an example where we try to sample from, so you have the diffusion coefficient here, this is a very academic, very simple example. This is parameterized by 4 parameters, and then you try to infer those 4 parameters from some measurements. The measurements are point measurements on a grid line by line, so 89 evaluations of the solution with Gaussian noise, and we want to, so we use P1 finite elements and regular triangulation, or sequence of regular triangulations, and in this case we did a simple KDE, so kernel density estimation from the sample of the ensemble at the previous level. And what you see here, I'm plotting all the twin points over the history of the Markov chain, so Q1, Q0, Q2, Q1, Q3, Q2. And you see that in the first one, they are somehow spread around, so the difference is not small, but the more you advance, the more points you have on the diagonal. The points on the diagonal is where the chains are synchronized, because then they are equal. Okay? So the more you advance, the more points you have on the diagonal, the more few points are off diagonal, so the variance of the difference is indeed small. And gets smaller and smaller over and then this and they also decorrelate faster. So the chain at level 0 and 1 have so this is the autocorrelation function. This shows how fast the chain decorrelates in time. You see that at level 3 decorrelates pretty fast. So you also improve the mixing by this construction. Okay, I think that was it. You again have some references here on the filtering and the multilevel MCC. Thank you for your attention.